Microsoft's Azure machine learning environment provides a mechanism to implement a variety of AI services. Azure has several different services for implementing machine learning. For example, with Azure, you can implement automated machine learning. Automated machine learning is a process by which you can actually automate the development of machine learning models. The advantage with automated ML is lots of the heavy lifting is handled for you so that you can focus on the model building, while Azure handles making sure that those models are scalable, efficient, and of high quality. Another handy service is Azure's Machine Learning Designer. Designer is an interactive and visual design tool that allows you to drag, drop, and connect modules like datasets, transformers, and algorithms onto a canvas so that you can build up machine learning models. Azure ML also includes the ability to manage things like datasets and compute capacity. In fact, datasets can be created by packaging data in Azure's data storage services, while compute instances and even clusters can be configured as training environments. One of the other cool features in Azure ML is pipelines. Pipelines consist of datasets and other modules that all get linked up together so that you can train one or more modules. You can train individual pipelines as many times as you want with the same or different datasets to test trained models. Machine learning is a significant step in most AI endeavors. In Azure, you can make use of automated machine learning to help make the process easier and faster. Now, you can implement different kinds of automated ML depending on what you're trying to do. For example, you can implement a classification model. Classification algorithms are supervised machine learning techniques that use labeled datasets to train models. The trained models are then applied against real data. This type of model can be used for things like fraud detection, handwriting recognition, and object detection. For example, imagine a picture dataset of dogs and cats. A classification algorithm would be perfect for being able to go through that dataset and classifying each picture as a dog or a cat. You can also implement a regression model. Regression algorithms are also supervised machine learning techniques that use labeled datasets to train models. The difference here is that a regression model is used to find the correlation between dependent and independent variables. Put another way, a regression model is excellent for making predictions of how much or how many. For example, imagine a dataset of cars. A regression algorithm would be perfect for looking at specifications of a car and predicting what its price would be. And then we have time series forecasting. Time series forecasting is a more advanced regression problem solver. It can be used to generate high-quality time series forecasts. Machine learning also includes a feature called the designer. The designer is extremely useful for creating pipelines and managing the flow of modules towards the ultimate creation of a trained model. With the designer feature, pipelines can be built based on a collection of interconnected modules. The most common modules are datasets, transformers, and algorithms for model training. Of course, there are model training modules as well. Pipelines can be put together in all sorts of arrangements with the ultimate goal of being deployed and interacted with by external consumers. Then the consumers can use the deployed pipeline and the trained model therein to get back predictions in real time or as a batch process. Pipelines don't have to be used for model training, though they can be used for simpler tasks like data cleansing. Pipelines are pretty well useless without a dataset. Datasets are required for model interaction or even just for cleansing if that's what your pipeline's for. At the end of the day, there are three types of datasets. Training datasets are used during the model training process to help program the machine learning engine. Validation datasets are used to tune the parameters of model algorithms. And finally, test datasets are independent datasets that are used to assess the effectiveness of the trained model. These are usually referred to as gold standard datasets. Another thing the designer allows for is the ability to run pipelines against specific compute resources. These can be anywhere from simple, cheap training compute clusters, or they can be large-scale, widely distributed, always-on Kubernetes clusters. Now, as you use it more extensively, you'll find that the designer in Azure ML has quite a lot of other features too. For example, with the designer, you can choose to use a model that was trained outside of your Azure ML right in your pipeline. Of course, you can also train a model yourself by submitting experiment runs, and then you can use that model too. Either way, once you have a model, you can register it in Azure ML. And once a pipeline has been set up the way you like it, you can deploy it to an endpoint. Azure will then give your pipeline a REST API URI that allows your pipeline to be called from external sources. Then there's IoT module endpoints. These are actually Docker containers that can include the model, any associated scripts, and any additional dependencies. These endpoints can be placed on an IoT device so that your model can run on the edge. For machine learning to work, clearly data is necessary, and once again, Azure ML has us covered there too with lots of different ways to manage data. For example, with Azure ML, you can use data workflows to visually represent how a dataset and an ML solution are set up and configured. Believe me, it's super handy to be able to visualize data flow. Azure ML also includes the concept of data stores. Data stores are used to securely connect to external Azure storage accounts that might be housing some of your data. And datasets are the most integral thing to use with training and using models. Datasets are references to your underlying data in a storage service. Datasets are what's used by machine learning models. Every data store is pointed to by a dataset, but not every dataset points to a data store. And lastly, when it comes to data management, we have data labeling. Data labeling involves, well, adding labels to data in datasets so that they can be used for supervised learning. When we're executing pipeline runs, experiment runs, notebooks, and so on, Azure ML requires that we use an appropriate compute resource to facilitate those runs. Azure ML allows us to manage that compute in different ways for different purposes. For example, compute targets are machines that can be used to host deployments or run model training scripts. Compute targets can be local or even remotely managed machines. Compute instances are virtual machines or VMs managed by Azure ML that are preloaded with tools and environments specifically for performing machine learning. That means that sample notebooks can be run with very minimal setup. And lastly, compute clusters are clusters of VMs that provide multi-node scaling features. Compute clusters are much better suited for large jobs and production releases. Now, as you can tell from what we've talked about so far, pipelines are a pretty central part of Azure ML. It's where a lot of resources are managed or at least used. But there are actually different kinds of pipelines worth noting. For example, standard machine learning pipelines are used primarily for orchestrating model training and generally consist of data input, transformation, and flow into a model trainer. But there are also data factory pipelines. These are used for orchestrating data. So usually this just consists of data input and transformation, with an augmented data set being the output. As you can probably guess, a data factory pipeline can sometimes be the input to a machine learning pipeline. And finally, we have the DevOps pipelines. DevOps pipelines are used for code and application orchestration. A good example of this is continuous integration and continuous deployment, or CI/CD. DevOps pipelines generally consist of generating applications and services and then deploying them. Interfacing with Azure's machine learning capability is generally done via Azure's Machine Learning Studio, or ML Studio. ML Studio has a lot of features that'll help you through the process of implementing not just machine learning, but also all of the peripheral aspects that you'll need along the way. ML Studio breaks down into a few categories of features. For example, with Azure ML Studio, you can author learning projects in a variety of ways. This includes notebooks, which can be used to write and manage code, Designer for creating and managing pipelines, and Automated ML for creating machine learning projects automatically. ML Studio also offers the ability to manage supporting assets like datasets, experiments, pipelines, models, and endpoints. And of course, you can also manage supporting services too. Now that includes compute resources, data stores, and data labeling. And finally, ML Studio makes it possible for you to deploy machine learning pipelines for external use, as well as manage their lifecycle. Creating a machine learning workspace in Azure is a fairly straightforward process. In fact, it works like almost every other resource in Azure. So if you're familiar with Azure already, this will be old hat for you. The Azure Machine Learning Workspace is dependent on other resources though. So when you're creating the workspace, you'll need to create those resources too. The good news is that the creation screen for the ML workspace includes the ability to create those resources on the fly. Like any other resource in Azure, the ML workspace needs a resource group to exist in so that you can manage resources, costs, and permissions. For this, I have two recommendations for you. If you're playing around, I recommend that you put all of your needed resources into a single resource group. That way, when it's time to clean up, all you have to do is delete the resource group and everything will get deleted with it. But be very careful with your resource groups. It's not recommended that you put everything into a single resource group. It's a best practice to have one service or offering per resource group. For example, if you have an alerting service, it can go into one resource group. Then if you have a notification service, it can go into another resource group. And that allows you to manage things like scale, costs, and permissions per service. Another thing the ML workspace needs is a storage account. This is where all the workspace information like data store references are kept, and this can be a new or existing resource. Next, the ML workspace needs a key vault. This is where secrets, or really any sensitive information, is kept. Again, this can be a new or existing resource. Another resource ML workspace needs is application insights. Now, App Insights is used for logging and other monitoring needs, and it's an extremely valuable resource for troubleshooting and performance monitoring. Once again, this can be a new or existing resource. And finally, a container registry can be used for registering Docker images. This is technically not required if you're not going to end up using Docker, but if you do, this can be a new or existing resource. ML Studio has a wide array of features that can be used to configure and manage not only the machine learning needs, but also the peripheral supporting resources. One of the key categories of features provided by ML Studio is with regards to authoring. There are several key authoring services in ML Studio. For example, Notebooks is the closest to Metal feature in ML Studio, and they're very powerful. Notebooks are an open source web application that can be used to create and share documents, code, equations, visualizations, narrative text, or a combination of all those capabilities. Microsoft actually includes a whole host of sample notebooks that you can use as soon as you create your ML workspace. Another authoring feature is Automated ML. Automated ML is a process that allows you to automate the development of machine learning models. Automated ML lets you quickly create models for classification, regression, and forecasting. And finally, there's the Designer. The Designer feature provides a pipeline canvas that can be used to drag, drop, and connect modules like datasets, transformers, and algorithms so that you can visually represent and ultimately create machine learning models. Of course, it's very difficult to author any machine learning without the supporting assets. Fortunately, ML Studio includes a variety of features that let you manage the assets that are needed by any of the ML work that you're going to be doing. For example, with ML Studio, you can manage datasets. Datasets are references to, well, data. Datasets can be created by pulling in data from local files, associating to data stores, connecting to online web files, or even connecting to an open dataset from the cloud. ML Studio also allows you to manage experiments. Experiments provide information on runs, run statuses, logs, and metrics. Experiments can be created from notebooks, automated ML runs, or even pipeline runs, so it's good that there's a central place to manage them. Another type of asset that ML Studio lets you manage is pipelines. Pipelines generally consist of interconnected datasets and modules that all work together towards the goal of training one or more models. So while we use pipelines and experiments to try to train models, eventually we'll get to a point where we'll like a model enough that we'll be ready to select a few of them for continued use. ML Studio lets you manage your various models and even deploy them to the outside world. Which brings us to our last asset that ML Studio will help you manage, and that's endpoints. Endpoints are machine learning models that have been deployed such that they can actually be called by external third parties using a simple REST API endpoint and a key. Now, Azure ML Studio also includes a few built-in services of its own that you can use. For example, compute resources are essential for actually being able to run your machine learning experiments, models, and endpoints. Compute resources can be compute instances, compute clusters, inference clusters, which can use Azure Kubernetes, or even an attached external compute resource. The Data Stores service allows you to set up secure connections to external data sources. For example, you can connect your ML Studio instance to your own Azure storage accounts like Blob Storage, FileShare, Data Lake Storage, Azure SQL, MySQL, and so on. Now remember that every data store is a dataset, but not every dataset is a data store. And finally, the last service ML Studio includes is data labeling. Data labeling allows you to create projects that can be used by humans to help add labels to data in your datasets. These labels can be things like image classification, object identification, or instance segmentation. In this demo, we're going to create and configure an Azure machine learning workspace. To do that, we're going to use the Azure portal to create a machine learning resource. We'll know it's working once we've gone through the creation cycle and we can navigate to our workspace in the portal. Before we begin, you'll need to make sure that you have access to an Azure account. If you don't, you can create one for free at azure.microsoft.com/free. Okay, so the first thing we need to do is navigate to the Azure portal in our browser. Here we are. Now let's create an Azure resource. We'll do that by clicking on the Create Resource link in the middle of the page. You can also create a resource by selecting the hamburger menu in the top left and selecting the Create a Resource option from there. Now what we want to do here is create a machine learning workspace, so let's search for machine learning. Now let's select the machine learning resource. Then we click Create to get the process started. When we're creating a machine learning workspace, we're asked for a bunch of information about that resource. In fact, the machine learning workspace actually needs a bunch of other Azure resources in order to run properly. The good news is that the setup page here asks us to choose or create those resources. So what we're going to do here is create all the resources we need all at the same time. First, we're going to create a resource group. In my case, I'm going to name the resource group sbtest-rg. Good. Next, the page asks me for a name for my workspace. Well, I'm not very creative, so I'm going to call it sbtest-ml. Now, Azure tries to be really helpful here and automatically assumes that I'm creating some new resources, and it names those resources based on my sbtest workspace name. So I'm going to leave those as is. Now you can pick whichever region you want, but since this is temporary, I'm going to leave it as the default. Finally, we need to create a container registry. As with most things in Azure, names need to be globally unique, so I'll name my registry sbtestml and then add some random numbers so it more or less matches the other resources. Besides that, we're going to leave everything else as the defaults. Good. Now we're going to skip all the rest of the tabs here and go straight to the creation step. So we'll click on the Review and Create. And assuming there's no issues, we can click on Create. Now, the process may take a little while to complete, and technically this happens asynchronously, so you can go off and do other things. But while this is happening, we'll wait for this to be done. Perfect. Now our workspace is complete. So let's navigate to it and check it out. In this case, we can do that by clicking on the Go to Resource button, but obviously that button isn't what you see when you first sign into the Azure portal. So let's navigate to it fresh. First, let's click on the Home link at the top of the page. This would be like we first signed in. Now right in the middle of the screen, I can already see my sbtest-ml machine learning resource. This is a list of your most common resources, so we could click on that right away if we wanted to, but then again, your resource may not always be in this list. So let's do this a different way. Let's click on the hamburger menu in the top left. In this menu, one of the options is Resource Groups, so let's click on that. Now this shows us all of the resource groups in the directory. In this case, I only have one, my sbtest-rg resource group. So find your resource group and let's click on it. Now the first thing that we see when we click on a resource group is its overview blade and all of the resources inside that resource group. And here we see all of those resources that were automatically named for us. That container registry we created with the random numbers, and huzzah, our machine learning resource. So let's click on our machine learning resource. And there we go. Our machine learning resource includes all sorts of blades with all sorts of different information and capabilities from access control to monitoring. So congratulations, you've created a machine learning workspace. In this demo, we're going to inspect the Azure ML Studio sidebar components so you can understand where to find the various tools and components needed for creating machine learning workflows. We'll do that by simply clicking through each of the sidebar options in ML Studio. Alright, so first we need to head over to the ML Studio in our browser. Perfect. Now you'll see along the left-hand side that there's a menu of options that are all categorized. At the very top, we have the Home menu option, and this is the default option that's selected when we first navigate to the ML Studio. In the home screen, we have a bunch of quick links to get started on some work. At the top of the screen, you can quickly create various resources by clicking on the big Create New Plus button. Then there's quick access to notebooks, automated ML, and the designer. And we'll get into those in a minute. Underneath all of that, we have a list of all the most recent runs that we've performed and even the compute that we've created. We can go directly to those screens by simply clicking on them. Then at the very bottom is quick access to tutorials that we can use to get started on specific things that you might want to do. Now let's go top to bottom on the sidebar and see what each of these options do. The first section that we see after Home is the Author section. This includes options that are used for creating actual machine learning models. The first option is Notebooks, so let's click on that. Notebooks are an open source web application that can be used to create and share documents, code, equations, visualizations, narrative text, or a combination of all those capabilities. Microsoft actually includes a whole host of sample notebooks that you can use as soon as you create your ML workspace. In fact, if you click on the sample notebooks at the top of the screen, you can see a list of a couple of folders. One for how to use Azure ML and one for tutorials. If you expand the tutorials folder, you can see a good set of different tutorials that you can use to get started. Now you can clone any folder into your own local files, and most of the samples will let you get started with minimal effort. The next option is Automated ML, so let's click on that now. Automated ML lets you train and find the best possible model for a given dataset based on several different algorithms and methodologies. You can run a regression test, a classification test, or even a forecasting test. And you can do all of that without writing a single line of code. Just give it data and off it goes. And we'll look at this in a bit more detail in another demo. The next option is Designer. So let's go ahead and click on that option. The Designer is a way to access and manipulate pipelines. With the Designer, you can drag, drop, and connect modules like datasets, transformers, model trainers, and algorithms in an easy-to-use canvas. You can arrange these modules to train models and manipulate datasets however you deem necessary. This is the tool that you'd use if you didn't want to automate the machine learning with automated ML. Now after the Author section, we find the Assets section. This is where all the resources and, well, assets that are used to support the actual machine learning authoring can be found. Unsurprisingly, the first item we see in the list is Datasets, so let's go ahead and click on that. The Datasets option shows us all the datasets that have been configured in ML Studio. From here, we can access all of our datasets. We can also create new datasets by clicking on the Create Dataset option at the top of the screen. In fact, let's click on that button for a second. The Create Dataset button requires that we choose one of four options. We can choose to create a dataset based on files that we have locally, meaning I can upload a dataset, or we can choose to associate a dataset to a data store, or we can choose to create a dataset based on files available online, or we can even choose to create a dataset based on an open dataset available in the cloud. Datasets are the lifeblood of machine learning, so this will be an area that you'll use a lot. The next option is the Experiments option, so let's click on that now. The experiment screen lists all of the experiments that we've ever created. Each experiment contains runs. Usually an experiment contains many runs. An experiment is all about trying to find the best fit model for your data. Experiments are a good way to group all of your runs together so that you can quickly figure out which one is best. After experiments, the next option is Pipelines, so let's click on that. Pipelines is sort of another way to look at information. At the top of the screen, there are three tabs: Pipeline Runs, Pipeline Endpoints, and Pipeline Drafts. Each time we run a pipeline, it will be shown in the Pipeline Runs tab, and this gives us a shortcut to specific runs that we might be interested in. There's also a way to go to the experiment that run belongs to. Meanwhile, the Pipeline Endpoints tab lists all the pipelines for which an endpoint has been created, and that means that any pipeline listed in this section is actually available to be run from outside ML Studio. And the last tab is Pipeline Drafts. This tab shows us a list of all the pipelines that we can edit. In fact, clicking this tab is basically no different than clicking the Designer option under Authoring. The next option in the list is Models, so let's click on that. The model screen shows us a list of all the models that we've created so far. Experiments and automated ML runs, which are just shortcuts to experiments, will create models. Each model will have information like which experiment it belongs to, when it was created, and whether or not there are any associated endpoints. If you have a model you like that you want to deploy, you can access that model and choose to deploy it, and we'll talk more about that in another demo. Next up, we have the Endpoints option, so let's go ahead and click on that. Endpoints are effectively deployed models. When an endpoint exists, it means that there is a publicly accessible REST URL that external people can use to access and run a model. Not just anyone can access the endpoint, of course. To access an endpoint, you need not just a URL, but also a key, and you can use this screen to reset those keys as well. Now, after the Assets section, we find the Manage section. This is where we can access and manage some of the services that were built into ML Studio. At the top of the list is the Compute option, so let's click on that first. The Compute section is where we can manage and configure all of the computing power that we'll need to perform some of the actions we'll be doing in ML Studio. The first tab is Compute Instances, and this is where you can set up VMs that you can use for things like notebooks. The next tab is the Compute Clusters. This is where you'll set up clusters so that you can run experiments. And the next tab is Inference Clusters. This is where you can attach external clusters like the Azure Kubernetes service. And finally, there's the Attached Compute tab. This is where you can attach your own external compute systems like VMs, HT Insight, Azure Databricks, and so on. Now the next option in the list is Data Stores, so let's go there now. Data Stores is where you can set up secure connections to external data sources like Azure Blob Storage, Azure File Share, Azure SQL, and so on. Creating a data store means that you'll be creating a dataset to access it. And finally, let's click on the last option in the list, Data Labeling. This is where you can create labeling projects. Labeling projects are ways for you to be able to give people access to datasets and have them go through each item in the dataset and provide labels. These people are usually referred to as labelers. Labeling projects give you the ability to send out links to people to perform labeling while you can gauge the progress of that labeling. This includes knowing how much of the dataset has been labeled and how many people have gone through and labeled the data. One area of Azure's AI that's worth talking about is Azure Computer Vision. Computer Vision deals with visual processing. For example, the Seeing AI app from Microsoft is an AI implementation that's designed to help people with vision impairment. The AI within that app works to take in the visual world and describe what it sees. To help with the Computer Vision AI, Microsoft has implemented the Azure Computer Vision service, and there are lots of capabilities built into that service. For example, the Custom Vision service uses images that you provide to train your own custom image classification and object detection models. This is actually very common. Imagine walking into a facility, scanning that facility with a camera, and then being able to pick out what's a pump, what's a compressor, what's a door, and even what shouldn't be there. And that's just it. The main feature of the Computer Vision service is to be able to analyze not only images but also videos. The service can scan various media to identify tags, descriptions, objects, and text. The service also includes a facial recognition service that can be used to create, well, facial recognition solutions. And one very interesting use case for computer vision services is form recognition. The form recognition service is pretty cool because it can be used to pull data from scanned forms like documents and invoices. Now, if you want to perform any image or video-based AI, the Azure Computer Vision Service has loads of useful features for you. For example, optical character recognition involves being able to extract printed or even handwritten text from images, and not just from plain, simple black and white images of documents like invoices and bills. We're talking about things like license plates, containers, and other real-life media. Computer vision also includes a feature for common object detection, and that means being able to identify everyday objects in an image. Common object detection will scan media and return bounding boxes for objects it identifies, along with a classification label and relationships to other objects. Another useful feature is brand object detection. That feature can be used to identify specific brands that are present using a logo database. This is valuable for situations where brands need to be scrubbed from images. Another feature of the computer vision service is that it can be used to automatically identify and return tags for recognizable objects found within an image, such as living beings, scenery, and even actions. And that's the whole point, isn't it? You say, "Here's a picture, tell me what's in it," and AI says, "Well, there's a house, a tree, a dog, and Freddy Krueger." The computer vision service can also be used to identify taxonomy-based categories detected in an image. This includes things like food, people, animals, plants, and so on. And next, a computer vision service includes features that can analyze any image and return a list of human-readable descriptions for that image. These descriptions can then be ordered from highest to lowest confidence level. So for example, you can provide an image of a crowd of people, and AI could look at that image and the various details therein and tell you that it's a sporting event, a rally, a protest, or a Kardashian birthday party. But wait, there's more. Probably the most ominous and obvious feature of the computer vision service is that it can detect human faces. That service can be used to predict age, gender, and a boundary box for any face it's given. The service is powerful enough that many faces can be identified at the same time from a single image or video, and that the results can return in a list. The service also includes simple features designed to make life a little easier when we're talking about significant scale of image analysis. For example, the computer vision service can analyze a given image and simply determine if it's something that can be classified as either normal clip art, good clip art, non-clip art, or ambiguous. Of course, you can also use the computer vision service to perform scoped analysis to scan images for domain-specific content, like celebrities or landmarks. And yet, there are still more features. An interesting feature of the Azure Computer Vision Service is that it can be used to detect the color scheme of an image and then identify the dominant foreground color, the dominant background color, and the set of dominant colors in general. And this is pretty cool if you want to apply themes or complementary colors for marketing. Next, you can use the Computer Vision Service to create intuitive, smart cropped thumbnails. This service can take images and crop them based on what it perceives to be the identified area of interest. It's not always just the middle of the picture. And finally, computer vision services can be very useful for detecting adult material in images. The results of that identification can then flag content as adult, racy, or even gory. And each classification includes a score so that you know just how adult, racy, or gory the image is. See, I wasn't lying. The Azure Computer Vision Service has tons of features. The Azure Custom Vision Service is an image recognition service. This service allows you to create and deploy your own image identifiers and improve them as you learn more. The service also lets you specify your own tags or labels, and then use those tags to train custom models. The Custom Vision Service has two main project types that you can create: a classification project and an object detection project. Classification projects can be either multi-label or multi-class. Multi-label projects allow you to add multiple tags to each image, while the multi-class project only allows a single tag per image, and we'll get to that in a bit. Each project requires information about the domain it serves, and this helps the service to optimize for the intended use. For example, your project could be about food, landmarks, retail objects, or yes, even generic domains. So just what is a classification project? Well, primarily a classification is a type of machine learning that's used to predict some category or class to which an item belongs. Let's assume, for example, that the classification we're talking about is diabetes, and whether or not a person is diabetic. For example, you could apply the features of a patient like age, weight, blood pressure, and a whole host of features to decide the likelihood that a patient is diabetic. In this case, the classification would be diabetic or not diabetic. Classification algorithms use the training dataset to predict a class for each item in the dataset. So for example, I may have a database of patients and I need to go through each of the patients in the dataset to determine if they're diabetic or not, and that would be a classification. In a classification algorithm, the training data is used to create better boundary conditions for deciding which class a particular item belongs to. Then, once boundary conditions have been determined by the model based on items in a training dataset, then those boundary conditions can be applied to predict a target class for new data. The Custom Vision service offers the ability to perform object detection. So you're able to create your own custom object detection projects. Object detection projects have a couple of core features. Specifically, an object detection project can analyze images for domain-specific content. This includes things like celebrities, landmarks, food, and so on. This is achieved by using scoped analysis of the images. In other words, the service looks specifically for those things. Once objects are found in the given images, the Custom Vision service can then return the coordinates of where in the image the objects were found. The returned information comes back as a list, in case there were multiple finds in the image. Each object found includes labels about what the object is expected to be. So AI can tell you, this picture contains the Eiffel Tower over here in the back, Brad Pitt here on the left, and Carrot Top here on the right. If the intent is to be able to classify images, then you can only do that with classification projects in the Custom Vision service. Classifying images is a very useful feature and much more common than you might think. Classification projects are broken down into one of two categories, multi-label or multi-class. A multi-label classification project is used when a sample image needs to be given multiple tags to describe it. For example, you could scan a news article and tag it as being about a place, a person, and an event all at the same time. Meanwhile, a multi-class classification project is used when each sample image can only be assigned a single tag to describe it. For example, you could look at a set of images about house pets. Now, each image would be a dog, a cat, or a fish, and so on. But an image could not be a dog and a fish. So you can only give an image a single tag. I mean, obviously you could tag an image as being a dog and an animal, but if the purpose of the image classification is to say what an image is, then you use a multi-class classification project. When you set up a project in a Custom Vision service, it can be optimized to find certain objects in images. That optimization is based on what's called a domain. There are several different kinds of domains that a project can be optimized for. For example, the general domain is a sort of catch-all that's optimized for quite an array of image classifications. This is what you would use if you're just not sure of which domain to use. Meanwhile, the food domain is optimized to find food dishes as generally displayed on restaurant menus. The landmark domain is optimized to identify not just famous landmarks, but any sort of natural or artificial landmark. The service works best when the landmark is prominent in the image. Meanwhile, the retail domain is optimized for images that are generally posted in shopping catalogs or websites. The logo domains are used for identifying specific brands that are present in an image. And of course, the adult domain is used for finding adult content in images. And finally, there are compact domains. Compact domains are optimized to run on mobile or edge devices, and they can be exported to run locally on those systems. Another core feature of Azure's computer vision service offering is the face service. The face service can be used to detect, and you'll never guess this, that's right, human faces. The service can find faces and then return rectangular coordinates of their location in the images, along with some various optional attributes. An API called the Face Verification API can compare two detected faces, or just one detected face and a comparison image, and analyze if the two faces are the same person. This is particularly useful for security situations. Another API called the Find Similar API can match a target face against a set of candidate faces and then filter out identical face images. And still another API called the Group API is able to partition a set of unknown faces into groups based on similarities. And finally, the Identify API can be used to detect a face within face images stored in a database. Facial recognition is actually not as hard as you might think. Facial recognition is done by identifying landmarks on a person's face, mapping them out into coordinates, and then comparing those coordinates to other already mapped out faces. So the trick is actually just finding the landmarks. And there are 27 predefined landmarks on a regular human face. This includes where your eyebrows are and how big they are, and where your eyes are and how open they are, information about your pupils, the size, shape, and position of your nose, and even the size, shape, and position of your mouth. All of this information is split into left versus right and top versus bottom. So the bottom lip versus the top lip, the right nostril versus the left nostril, it all matters. The coordinates for each facial landmark are then returned in units of pixels for processing. Now, once a face has been broken down into landmarks, each landmark coordinate can then be assessed to determine information about the subject the face belongs to. As humans, we see these things somewhat intuitively, but AI is able to take that information and make it somewhat formulaic. For example, with landmark information, the Face Detect API can generally estimate what the gender of the subject is. This can be male, female, or even genderless. It might seem obvious that the API can also detect if the subject is wearing glasses, but it's actually smart enough to determine if the glasses are reading glasses, sunglasses, or even swimming goggles. The API can also assess things with regards to hairline. The API can detect if hair is visible, bald, or even what hair color it is. And another neat attribute the API can detect is something you wouldn't normally expect, and that's the head pose. The pose can be described by the pitch, roll, and yaw angles, and this information is given in degrees. Another attribute the API can estimate is the age of the subject, but I wonder if it can guess the age of Keanu Reeves or Nicolas Cage. Not all of the facial pictures that the API is going to get are going to be top-notch. They can't all be winners. So another attribute that the API can return is the overall blurriness of the face. The value is given between 0 and 1 and has an informal rating of low, medium, or high. Now, as humans, we're instinctively capable of detecting the emotions of another human through the slightest facial expressions. Well, AI is coming along even in that category too. In fact, the Face Detect API is capable of predicting the emotions of a subject along with a confidence level. Now, all the possible emotions are scored and total up to a value of 1. So think of a pie chart. You could be surprised, fearful, and happy at the same time if you're on a roller coaster, right? So you can map out the total amount of emotion that you have in each category on a pie chart. API is then able to detect emotions like happiness, sadness, anger, contempt, disgust, surprise, fear, and yes, even neutrality. Can you imagine a neutral person on a roller coaster? Well, if I don't survive this, tell my wife I said hello. Another attribute the Face Detect API can find when analyzing an image is actually the exposure of the image. Just like blurriness, the photo itself can be problematic. The exposure value is given between 0 and 1 and has an informal rating of underexposed, good, or overexposed. The Face Detect API can also unsurprisingly detect facial hair, and this can include its presence, its length, its color, and even its type. And of course, the API can also detect makeup, but it can actually categorize that makeup into a set of Boolean values for everywhere that it can be applied. So you can see values for eye makeup and lip makeup. And just like the blurriness and exposure, the Face Detect API can detect if the image has any noise in it that could affect the quality of the results. The noise value is given again between 0 and 1 and has an informal rating of low, medium, and high. The Face Detect API can also detect if there are any objects obstructing parts of the face. A common reason for that is hair hanging over someone's face, but it could just as easily be someone in a shadow, behind a post, or so on. These occlusions can be detected, and each part of the face that's obstructed is included in a Boolean output. And finally, the Face Detect API is quite capable of detecting your smile. Isn't that nice? There are lots of different smiles. You can have a cheerful smile, a contemptuous smile, a flirtatious smile, a wry smile, a playful smile, a sincere smile, a smug smile, a worried smile, a smirk, or even an arrogant smile. Whatever kind of smile you have, the API will return a value between 0 and 1 that indicates no smile, all the way up to a clear smile. Another core feature of Azure's computer vision service offering is the Form Recognizer service. The Form Recognizer is used to identify and extract information from forms, tables, and other structures. The Layout API in the Form Recognizer service finds and extracts texts, tables, selection marks, and even structure information from documents and images, and then returns the extracted data as a structured JSON model. You can actually create custom models using your own forms. Only 5 sample forms are needed to get started. Once the model is trained, the model can be continuously tested and retrained to get better at recognizing form data. That training can be performed using labeled or even unlabeled data. And of course, you don't have to build your own custom models. Pre-built models are also available for common things like invoices, receipts, and business cards. The Layout API is the key service in the Form Recognizer service. The Layout API analyzes formatted documents and returns structured JSON data to describe what it found. The Analyze Layout process of the API is able to kickstart the data extraction process for given documents. The API actually returns a response header that includes an operation location and a result identifier. That means that the API is kicked off and the work happens behind the scenes. You don't have to wait for the API to respond with the results. Instead, you're given information on where to go to find the results when the operation is complete. And that brings us to the Get, Analyze, Layout Result process. That process uses the result identifier from the Analyze Layout process and returns a JSON response object that includes a status of how the process is coming along. The status can be not started, running, failed, or succeeded. Now, once the process is complete, the JSON output will then include a section called Read Results, which will contain the text, selection marks, and whatever else was found in the given documents. Now, the Layout API is able to analyze all sorts of different documents and images, but there are limits and constraints. For example, the Layout API only supports certain file formats. That includes JPEGs, PNGs, PDFs, and TIFF files. So you won't be able to pass in a docx or a txt file. The size of the file is also limited. Specifically, only the first 2,000 pages of PDF and TIFF files will be processed. So if you have a document that's larger than that, you'll have to split it up. Though I'd be willing to bet that a 2,000 page limit would be more than enough to handle 99% of the cases, and then some. There are also limitations on the physical dimensions of any images that are given. So the minimum dimension for an image is 50 by 50 pixels, and the maximum is 10,000 by 10,000 pixels. But no matter what, the image must be less than 50 megabytes in size. And PDF documents also have maximum dimensions, not just images. The maximum dimensions for a PDF is 17 by 17 inches. Now, as I mentioned earlier, you can use pre-built models in Form Recognizer to analyze and scan common forms like invoices, receipts, and business cards. This is a very handy tool to use, and you can imagine how useful that would be for businesses, particularly as it relates to tracking expenses. The pre-built invoice model can be used to extract invoice data from just about any invoice form. The model then returns a structured JSON response that describes the content that was found in the invoice. So you can see the line items, the total charge, taxes, and so on. And it's actually optical character recognition, or OCR technology, that's used when scanning an invoice, along with a specific deep learning model to extract the main information from the invoice. Now, the data that's extracted from an invoice should be everything that may have potential value to you. This includes text, tables, invoice ID, invoice date, customer name, amount due, taxes due, ship to, and bill to details. Then all of that extracted data is then returned in a structured JSON format. Once the data has been digitized and put into a JSON structure, it can be easily processed by any software to kick off any other automation that you might need. So let's talk about what the JSON structure of an invoice would look like. What would we actually see in there? Well, the JSON structure actually includes three main sections of data. Specifically, the read results section holds all of the recognized text values. Now, these values are further organized by page, line, and words. The page results section holds all of the tables and cells that were found in the document. This also includes information like their bounding boxes and confidence level. And finally, the document results section holds all of the specific values for the invoice. This includes things like the customer name, customer ID, purchase order, invoice ID, and so on. When we use Azure Machine Learning Workspace and Studio, we can do lots of things to create, train, and deploy models. You can run pipelines, you can run experiments, and we can manipulate and categorize data. All of these activities require a certain amount of compute resources in order to execute, and there are actually a few different kinds of compute available in ML Studio. For example, compute instances are virtual machines or VMs managed by Azure ML and are preloaded with tools and environments specifically for performing machine learning. This means that sample notebooks can be run with very minimal setup. Meanwhile, compute clusters are actually clusters of VMs that provide multiple node scaling features. Compute clusters are much better suited for large jobs and production releases. Inference clusters are machines that can be used to host service deployments or run training scripts and be a local or remote machine. And finally, you have the option of attaching compute to ML Studio. Attached compute links the system to existing Azure compute resources such as VMs or Azure Databricks. Of course, there's no getting around the fact that machine learning requires data, and ML Studio allows you to feed data into the system using datasets. But when a dataset is created, it must be categorized into one of two types. The first type is what's called a file dataset. A file dataset is a dataset that contains, well, files. These files can be locally sourced through a data store, or they can be a reference to a public URL. The next type is what's called a tabular dataset. A tabular dataset is a dataset that contains data in a standard table format, meaning it has rows and columns. Tabular datasets can be created from CSV, TSV, SQL query results, or just about anything so long as it's returned in a tabular format. The type of dataset matters quite a lot for the type of modeling you're going to want to do. For example, if you want to categorize images, you'll have to use a file dataset. But if you want to predict the price of cars, you'll have to use a tabular dataset. Now, ML Studio has a wide array of features that can be used to configure and manage not only the machine learning needs, but also the peripheral supporting resources. And one of the key categories of features provided by ML Studio is with regards to authoring. And there are several key authoring services in ML Studio. For example, Notebooks is the closest to Metal feature in ML Studio, and they're very powerful. Notebooks are an open source web application that can be used to create and share documents, code, equations, visualizations, narrative text, or a combination of all those capabilities. Microsoft actually includes a whole host of sample notebooks that you can use as soon as you create your ML workspace. Automated ML is a process that allows you to automate the development of machine learning models. Automated ML lets you quickly create models for classification, regression, and forecasting. And finally, there's the Designer. The Designer feature provides a pipeline canvas that can be used to drag, drop, and connect modules like datasets, transformers, and algorithms so that you can visually represent and ultimately create machine learning models. Of course, it's very difficult to author any machine learning without the supporting assets. Fortunately, ML Studio includes a variety of features that let you manage the assets that are needed by any of the ML work that you're going to be doing. For example, with ML Studio, you can manage datasets. Datasets are references to, well, as we said before, data. Datasets can be created by pulling in data from local files, associating to data stores, connecting to online web files, or even connecting to an open dataset from the cloud. ML Studio also allows you to manage experiments. Experiments provide information on runs, run statuses, logs, and metrics. Experiments can be created from notebooks, automated ML runs, or even pipeline runs. So it's good that there's a central place to manage them. Another type of asset that ML Studio lets you manage is pipelines. Pipelines generally consist of interconnected datasets and modules that all work together towards the goal of training one or more models. So while we use pipelines and experiments to try to train models, eventually we'll get to a point where we'll like a model enough that we'll be ready to select a few of them for continued use. ML Studio lets you manage your various models and even deploy them to the outside world. Which brings us to our last asset that ML Studio can help you manage, and that's endpoints. Endpoints are machine learning models that have been deployed and that can actually be called by external third parties using a simple REST API endpoint and a key. Now, Azure ML Studio also includes a few built-in services of its own that you can use. For example, compute resources are essential to actually being able to run your machine learning experiments, models, and endpoints. Compute resources can be compute instances, compute clusters, inference clusters, which use the Azure Kubernetes service, or even an attached external compute resource. The Data Stores service allows you to set up secure connections to external data sources. For example, you can connect your ML Studio instance to your own Azure storage accounts like Blob Storage, FileShare, Data Lake Storage, Azure SQL, Azure MySQL, and so on. Remember that every data store is a dataset, but not every dataset is a data store. And finally, the last service that ML Studio includes is data labeling. Data labeling allows you to create projects that can be used by humans to help add labels to data in your datasets. These labels can be things like image classification, object identification, or instance segmentation. When we use Azure's Machine Learning Workspace and Studio, we can do lots of things to create, train, and deploy models. We can run pipelines, we can run experiments, we can manipulate and categorize data, and all of these activities require a certain amount of compute resources in order to execute. And there are actually a few different kinds of compute available in ML Studio. For example, compute instances are virtual machines or VMs managed by Azure ML that are preloaded with tools and environments specifically for performing machine learning. That means that sample notebooks can be run with very minimal setup. Meanwhile, compute clusters are clusters of VMs that provide multi-node scaling features. Compute clusters are much better suited for large jobs and production releases. Inference clusters are machines that can be used to host service deployments or run in training scripts and can be local or even remote machines. And finally, you have the option of attaching your own compute to ML Studio. Attached compute links the system to existing Azure compute resources, such as VMs or Azure Databricks clusters. So let's dive into these a little bit. Compute instances are fully managed virtual machines in the Azure cloud that are specifically optimized for machine learning. Compute instances offer several benefits. For example, productivity is increased because it means that you can fully integrate notebooks that make use of built-in Jupyter, Jupyter Lab, and RStudio. So rather than having to jump from one system to another, you can stay within the same environment and do all of your work. Now with compute instances, security support is also provided for auto-provisioning, role-based access control, virtual network support, and SSH policy access. In other words, the VMs are fully managed by Azure, and you don't have to worry about their security so much. In ML Studio, compute instances are also pre-configured with needed machine learning packages, deep learning frameworks, and GPU drivers, so you don't have to create your own VMs and configure them. ML Studio takes care of all of that for you. And finally, compute instances are super easy to customize for CPU and GPU resources, VM size, and number of available cores. It's literally just a pick list. Meanwhile, compute clusters are clusters of VMs that provide multi-node scaling features. Compute clusters are much better suited for large jobs and production releases. and they have lots of useful features too. For example, a compute cluster can be a single or multi-node. You can configure the number of nodes you want in the cluster at any time. So depending on the work you want to do with the cluster, you may set it up to have a single node or much more. The best part of compute clusters is that they can be set up to auto-scale, and that means that the more compute power is required to run a job, nodes can be spun up to facilitate that demand. And you're in complete control of the minimum and maximum nodes in the cluster so you don't get overcharged. Clusters are complicated things to manage, but with ML Studio, cluster management and job scheduling is handled automatically by Azure. All you have to do is specify how many nodes you want, and Azure will take care of the rest. And finally, just like with compute instances, you can also easily configure your desired CPU and GPU processors that you want for your cluster to use. And just like with instances, it's super easy because it's just a pick list. Inference clusters are machines that can be used to host service deployments or run training scripts that can be local or even remote machines. When you're running an inference pipeline, a local web service can be used for testing, debugging, and troubleshooting. Of course, you can go to the other extreme and implement an Azure Kubernetes Service or AKS. AKS is generally used for real-time inferences and supports GPU and field programmable gate arrays, or FPGA. AKS is typically used for high-scale production deployments. An alternative to AKS is Azure Container Instances, or ACI. Like the local web services, ACI is generally used for testing and development, and are pretty good for workloads that require less than 48 gigs of memory. The difference is that ACI is hosted by Azure versus your own local web service. Now, it's worth noting that Azure ML compute clusters are used for batch inference and run batch scoring on serverless compute. You will not be able to select a compute instance when you choose to run pipelines or other inference jobs. Now, Azure ML Studio does allow you to bring your own compute to the party. If you don't want to use the compute that's built into ML Studio, that's fine. Perhaps you already have your own systems that you've built up and configured to your specific preferences or requirements. In that case, you can attach your own compute to the ML Studio so that you can reference it as part of your machine learning activities. So what kind of compute does ML Studio support for attachment purposes? Well, Azure VMs or even remote VMs can be attached as long as they have an IP and authorization credentials. Azure Databricks that use the Apache Spark-based environments in the Azure cloud can also be connected by using the compute name, the workspace name, and an access token. Next, you can attach Azure Data Lake Analytics to do analysis of big data. These can be connected by using the compute name, the resource group, and an account name. And finally, you can attach Azure HT Insights for performing data analytics and training data models. For machine learning to work, clearly data is necessary, and once again, Azure ML has us covered there with lots of different ways to manage data. For example, with Azure ML, you can use data workflows to visually represent how a data set and an ML solution are set up and configured. And believe me, it's super handy to be able to visualize data flow. Azure ML also includes the concept of data stores. Data stores are used to securely connect to external Azure storage accounts that might be housing some of your data. Data sets are the most integral thing that you can use with training and using models. Data sets are references to your underlying data in a storage service. Data sets are what's used by machine learning models, and every data store is pointed to by a data set, but not every data set points to a data store. And lastly, when it comes to data management, we have data labeling. Data labeling involves, well, adding labels to data in a data set so that they can be used for supervised learning. Now, data stores are used to securely connect to external Azure storage accounts that might be housing some of your data. Data stores are data sets, but not all data sets are data stores. So what kind of data stores are there? Well, first we have Azure Blob Storage. Blob storage is optimized for massive amounts of unstructured data. That data can be simply text or it can be binary data such as images, videos, audio files, database backup files, and so on. Put simply, blob can be anything. Then we have Azure File Share. File shares are fully managed network file systems in the cloud. It's as simple as that, file storage. Next, there's Azure Data Lake Storage Gen 1. Data Lake 1 is a hyperscale repository that's used for big data analytics workloads. Data Lake can store literally petabytes worth of files. But there's actually a Gen 2 for Data Lake Storage too. Gen 2 is generally similar to Gen 1, but it also provides a hierarchical namespace for Azure Blob Storage. Data stores can also point to Azure SQL databases. Azure SQL databases are most often used for lift and shift scenarios, but they still are very good at storing and optimizing relational data. Azure SQL is a fully managed PaaS database and always runs the latest stable version of SQL Server. Now, along the same lines as SQL, you can also connect to an Azure PostgreSQL. Azure PostgreSQL is a relational database based on the Community Edition version. Now, data stores can also connect to Azure MySQL databases. Now, Azure MySQL is another relational database based on the MySQL Community Edition version. And finally, we have the Azure Databricks file system, or DBFS. DBFS is a distributed file system which is mounted on an Azure Databricks workspace and is made available on Azure Databricks clusters. Now, when we embark on our supervised machine learning journey, we're really talking about using and manipulating data sets. Now, obviously we need data for learning, but there's other data sets that we need too. For example, the most obvious kind of data set that we need is a training data set. Training data sets are used during the learning process to help build a model and ultimately program the machine learning engine. But how can we know that our training is any good? Well, that's where validation data sets come in. Validation datasets are used after a model has been trained to compare the trained algorithm to more known data. A validation dataset is generally used to fine-tune parameters of a model algorithm. But even after a validation dataset, there's a test dataset. Test datasets are used as a sort of gold standard to determine the actual performance of a fully built model. Of course, there's no getting around the fact that machine learning requires that data. And ML Studio allows you to feed data into the system using datasets. But when a dataset is created, it must be categorized into one of two types. The first type is what's called a file dataset. A file dataset is a dataset that contains, as you can probably imagine, files. These files can be locally sourced through a data store, or they can be a reference to a public URL. The next type is what's called a tabular dataset. A tabular dataset is a dataset that contains data in a standard table format, meaning it has rows and columns. Tabular datasets can be created from CSV, TSV, SQL results, or just about anything as long as it's returned in a tabular format. Now, the type of dataset matters quite a lot for the type of modeling that you're going to want to do. For example, if you want to categorize images, you'll have to use a file dataset. But if you want to predict the price of cars, you'll have to use a tabular dataset. Now, when we're creating a dataset to use in ML Studio, we actually have the option to use Azure Open Datasets. Open datasets are references to external open source datasets. There are all kinds of open datasets that you can use. For example, weather datasets can be used by researchers who want to create ML models to analyze weather patterns. Available datasets include the NOAA Global Forecast System and the NOAA Integrated Surface datasets. This is particularly relevant in today's world of climate science. Satellite imagery datasets can be used by researchers who want to analyze changes to the Earth over time. Available datasets include the MODIS dataset and the NOAA Global Hydro Estimator datasets. This is another climate science relevant scenario. And a final example is socioeconomic datasets. These datasets can be used to analyze population data by U.S. zip code and county. Available datasets include the U.S. population by zip code, by county, and the U.S. Consumer Price Index. In this demo, we're going to create a pipeline in ML Studio to show how the Designer tool can be used to train a simple regression model. To do that, we're going to create a new pipeline through the Designer, and then we'll add and configure certain modules to show a generic regression pipeline. First, we'll need to access the ML Studio from our browser. So what we want to do here is we want to author a new pipeline and play around with some modules to see how they could connect with each other. To do that, we need to access the Designer section from the left-hand menu. So let's do that. Now the Designer screen shows us a list of all the pipeline drafts that we already have. In fact, that's what the Designer is doing. It's giving us the ability to manipulate pipelines and how they run. So what we want to do here is we want to create our own new pipeline. And to do that, we can simply click on the giant plus button at the top of the screen. And this will bring us to a brand new pipeline. So let's do that. Perfect. So now we're in the Designer. We have an empty canvas right in the middle, a list of modules that we can add from the Asset menu on the left-hand side, and some configuration information about this pipeline on the right-hand side. In fact, the right-hand menu is asking us to select a compute target for this pipeline. So let's do that first. We can do that by clicking on the Select Compute Target link. So let's do that. Now in this pop-up, we're asked to select a compute cluster to use for our pipeline, and that's important. If we run this pipeline, it will add that run to an experiment, and all experiment runs need to be run using a compute cluster. So with this dialog, we can select an existing compute cluster, or we can create a new one. Now I'm going to select my existing compute cluster and click Save. And now using the same configuration panel, I'm going to name my pipeline something that makes sense. I'm going to call my pipeline SB Test Pipeline Demo. And then I'm going to click Save. Perfect. Now we're ready to go. So let's build a pipeline. But what do we want to build? Well, remember that one of the usual purposes for a pipeline is to train a model. So let's train a model. But what should we train it to do? Well, let's do something easy to wrap our heads around. To get us started, I'm going to add a dataset to the canvas, and then I'll explain what we're going to do with it. Under the Sample Datasets section on the left-hand Assets menu, I'm going to find the Automobile Price Data module and drag it onto the canvas. Okay, so this dataset includes a list of a whole bunch of cars. We could explore that dataset from the screen, but let's keep this simple and you can trust me that it's all in there. The dataset includes information about each car, so things like seats, engine size, mile per gallon, horsepower, and so on. Now what we want to do with this pipeline is we can create a supervised machine learning algorithm that uses that dataset to predict the price of a car based on the information it learns from this dataset. So let's do that. Let's bring in a model training module. To do that, expand the model training section, find the train model module, and drag it underneath the dataset module. Now placement doesn't matter that much, but for readability, it's better underneath. Oh, and also leave a bit of room between the modules. Good. Now what we need to do is connect the dataset to the model trainer module. To do that, click on the output dot at the bottom of the dataset module and drag it down to the input dot on the right side of the model trainer module. The right input dot is the one used for datasets. Excellent. Now notice that the model training module has a warning symbol on it. Well, that's because we haven't told it what to train. So let's click on the module to select it. And now on the right-hand configuration panel, we can see that it wants us to select a column of data to train. So let's do that. Let's click on the Edit Column link above the Label Column field. Now remember that what we want to do is we want to have our model predict what the price of a car would be based on all the data in that dataset. So what we want to do here is select the Price column. So let's go ahead and do that by clicking on the field, scrolling to the bottom, choosing Price, and then clicking Save. Good. So now we have a dataset and we're training a model to predict price. Well, yes, but actually no. Our model training now knows what to predict, but it doesn't know how to predict it. In order for the model trainer to predict the price, it needs an algorithm to run. So we need to add an algorithm module to the canvas now too. Predicting a numeric output based on other features of a dataset means that a regression algorithm is probably best. We'll keep it nice and simple and we'll add a linear regression algorithm. So let's go back to the modules list and expand the machine learning algorithms section, search for linear regression module, and add it to the canvas above the model trainer. Excellent. Now we can connect it to the model trainer by dragging its output dot to the left input dot of the model trainer module. And that's it. At this point, we have the world's simplest pipeline that takes a dataset about cars and runs it through a model trainer using a linear regression to predict the price of a car. Now we can run this pipeline by clicking on the Submit button at the top of the screen. But I wouldn't bother with that. In real life, the dataset needs to be cleansed and normalized using transformers. We'd also want to score our model so that we know how well it's doing. Then we could even do some model evaluation. And all of these activities can be done simply by dragging in more modules and connecting them all up, just like we've done here. Great job. When we set about on our journey into model training, the primary question to ask yourself is, what sort of algorithm do I need? When it comes to machine learning, there are three main types of algorithms that you can choose from: regression algorithms, classification algorithms, or clustering algorithms. So let's dive into these a little bit. So just what is a regression algorithm? Well, primarily a regression model is a type of machine learning that's used to predict some value of an item based on various features of that item. Importantly, the value you're trying to predict is always a number. For example, let's assume that the item we're talking about is a car, and the value we're trying to predict is a price. We can use the various features of each car to determine an algorithm for predicting the price. So for instance, you could apply features like horsepower, number of seats, engine size, miles per gallon, and a whole host of other features to decide what a likely price is for that car. Now, regression analysis is a type of predictive modeling that calculates the correlation between dependent and independent variables. In other words, how do all these features of a car ultimately correlate with its price? And another aspect of a regression algorithm is that the prediction always falls somewhere on a continuous spectrum. In other words, it's a number. Put in plain English, a regression algorithm is typically used to answer the basic question of how much or how many. So what's a classification algorithm? Well, primarily a classification model is a type of machine learning that's used to predict some category or class to which an item belongs. So let's assume, for example, that the classification we're talking about is diabetes, and whether or not a person is diabetic. For example, you could apply the features of a patient like age, weight, blood pressure, and a whole host of other features to decide the likelihood that a patient is diabetic. In this case, the classification is diabetic or not diabetic. Classification algorithms use a training dataset to predict a class for each of the items in the dataset. So for example, I may have a database of patients, and I need to go through each patient in that dataset to determine if they're diabetic or not, and that would be a classification. In a classification algorithm, the training data is used to create better boundary conditions for deciding which class a particular item belongs to. Then, once boundary conditions have been determined by the model, based on items in the training dataset, then those boundary conditions can be applied to predict a target class for new data. Now, it turns out that saying that something is a classification algorithm is sort of vague. There are actually several different types of classification algorithms, though it's worth noting that they usually break down into one of three categories. The first type of classification is the binary classification. Sometimes this is referred to as a two-class classification. Ultimately, a binary classification algorithm can only have two possible outcomes. An example of this is classifying a light switch as being either on or off. Of course, if we have a two-class classification algorithm, then it stands to reason that we have a multi-class classification algorithm. And indeed we do. A multi-class classification system is quite simply used when data could be classified into more than just two possible outcomes. For example, if you were to look at a database of dogs and cats, then it would be a binary system because each is either a dog or a cat. But if you add hippopotamus to the mix, then suddenly there are more than two possible outcomes. So we're looking at a multi-class algorithm. And then comes the multi-label classification algorithm. In the binary and multi-class algorithms, a single data item can only have one possible outcome. However, with a multi-label classification algorithm, a single data item can actually belong to multiple buckets. For example, when we look back at our animal database, we would be able to not only classify those creatures by their type, but we could also have another label that says whether or not they're house pets. So now we could say that a hippo is a hippo, but definitely not a house pet. A house cat is a cat and definitely is a house pet. And then we have a lion, which is a cat, but definitely not a house pet. So now what's a clustering algorithm? Well, primarily clustering is a type of machine learning that's used to group similar items from a dataset based on various features of those items. Importantly, what you're trying to do is find a logical grouping for the items in the dataset. For example, let's assume that the item we're talking about is a penguin. What we'd be trying to do is group all the penguins in the input dataset into a certain number of logical groups. We can then use the various features of each penguin to determine an algorithm that can group penguins into appropriate clusters. For example, you could apply features like their flipper length, body mass, and a whole host of other features to decide what is a likely grouping for the penguins in that dataset. Clustering is an unsupervised learning technique that's often referred to as cluster analysis. Now, what makes the clustering algorithm unsupervised is the fact that it will use unlabeled data to try to determine logical groupings in the data. And in a clustering algorithm, these logical groupings of data are more accurately referred to as clusters. Clusters are then used for downstream feature engineering or pattern discovery. When it comes to clustering algorithms, there are a few different algorithm classifications. For example, the first type of clustering algorithm is density-based. Density-based algorithms are quite simple to wrap your head around. Basically, they just group based on high concentrations of data points that are separated by low concentration areas. So imagine you had a bunch of people go stand in a field, and then from an aerial view you could look down and just pretend to draw a line and group people accordingly. Of course, the problem with that is there's no real rhyme or reason to it other than that density. So if we got another dataset, we'd have to regroup people, but at least we'd be following the same principle. Then there's a distribution-based algorithm. These algorithms group data based on the assumption that each item is part of a cluster based on the probability that they belong to that cluster. And that's a pretty good algorithm to use. But as populations drift closer to each other, the probability that an item belongs to one cluster versus another becomes less well understood and closer to 50-50. Then there's centroids. Centroids are the geographic center of a population of data points. Centroid-based algorithms separate the data based on multiple centroids in the data. Next, there's a hierarchical-based algorithm. These algorithms basically just build a tree of clusters. Then you could look at an entire branch and say, that's a cluster. For example, you could look at the phylogenetic tree of life and classify life hierarchically. Creating a classification model experiment from scratch in Azure is actually a fairly straightforward process. You can go from having a fresh Azure account to running a classification model in just a few quick, easy steps. In fact, let me walk you through it. The first step is to create an Azure ML workspace, and this gives us access to ML Studio and manages the underlying resources that we'll need. Then we need a dataset. Well, a dataset can be found and uploaded using existing Microsoft samples. Then we can configure and run an experiment against that dataset using any type of compute that we need, and that can just be a simple VM. Once the experiment is run, we can view all the ML models that were created that fit the data that we gave it. And after we review the generated models, we can pick whichever one we deem to be the best one and then deploy it as a web service through a couple of simple clicks. And that's it. Once we're done and happy, we can then go ahead and clean up the work that we did. So how would we go about creating an Azure ML workspace? Well, like most things in Azure, that means creating a resource. So the first thing you would do is head over to the Azure portal via your browser. Then we'd select to create an Azure Machine Learning resource, and that would kick off the process of creating an Azure ML workspace. Of course, like any Azure resource, an Azure ML workspace needs a bit of information to get started. And the first thing it needs is a name for your workspace. Now, that name needs to be globally unique, so a naming convention is recommended. The workspace also needs to know what Azure subscription to use. And like any other resource, you need to specify a resource group to use from within that subscription. I highly recommend keeping your resources separated by service or purpose so you can delete them quickly just by deleting the resource group. The workspace also needs a location or a region. The available regions might be limited, and you want to remember about data transmission laws, so be very careful which region you pick. And finally, you can pick a workspace edition, and generally basic is good enough. Once the ML workspace is created, you can launch the ML Studio. And from the ML Studio, we can create and manage all kinds of things related to machine learning. Our plan is to get to the point where we can run an experiment. But like any machine learning project, we need data. So the first thing we'll need to do is create a dataset. And that's a fairly straightforward process too. There are actually a few ways that you can create a dataset. You can create a dataset directly, or you can create a data store, or you can use the automated ML feature in ML Studio to do all of that work for you. When you select to create an automated ML run, it will prompt you first for information about a dataset that you can simply select or upload. When we get to doing this, we'll create a dataset by entering information so that we can upload a sample tabular dataset. Now, as the dataset is uploaded, we'll be prompted to review the dataset settings so that we can align with whatever our experiment is going to be. The settings to review are the file format, the column delimiter, the file encoding, how to manage column headers, and whether we'll skip any rows. In most cases, the defaults are actually perfectly fine. Once the dataset settings are set, then we can review the details of the schema so that we can make sure we're uploading just what we want to column-wise. And we'll confirm the details of the dataset. And then we'll create the dataset. Now, during this entire process, we'll be constantly shown a preview of the dataset that we're bringing on board. Now, this might sound like a lot, but it's actually quite simple and really easy to walk through and create. Now, once the dataset is brought on board, the next thing the automated ML feature will ask us to do is actually configure an experiment to run against the dataset. Now, one of the bits of information automated ML will require is the compute cluster to run against. You can select an existing compute cluster, or you can actually create a new one on the fly. Now, when we get to doing this, we'll actually select a compute cluster on the fly to make our lives a little bit easier. Then we can select what type of experiment we want to run. That's the point in which we would select to run a classification experiment or a regression experiment. In our case, we'll pick a classification experiment. And as part of that, we can select the primary metric that we want to classify. We can also ask the experiment to explain the best model. We can select which algorithms to use or block. And we can select under which conditions to exit the run. We can also provide validation information. And we can specify concurrency information. And then we can finally run the experiment. Now, I say finally, but really the process is quite simple. Most of the settings are acceptable as the default. So running an experiment from the ground up is really not too difficult. The purpose of the experiment run is to generate a model from the input dataset, given the training criteria. When we use the automated ML feature, we're really letting ML Studio figure out most of the training for us. The result is that we'll actually get a few models being created. Then we can choose which model we like best. One way to look over the created models is to go to the Models section in ML Studio, and this will list all the models that have been created and tested in the system so far. They're usually ordered by metric scores, so the best model is at the top. You can also explore each model individually just by clicking on it. Then a bunch of information about that model will be presented. One of the bits of information is the algorithm name that was used to generate that specific model. You can also see all the performance metrics associated to the algorithm so you can see how good it actually was. Just because a model is at the top of the list doesn't mean it's any good, so it's always a good idea to look over those metrics. In fact, reviewing all of the details and metrics and charts associated to the model is a good idea, particularly if your intent is to put that model out into the wild. You'll want to know how good it really is. Anyway, once the experiment has been completed by the automated ML feature, it will show you all the models it ran, and it will also show you the best model it came up with. You can then use the experiment view to select the model and deploy it as a web service. Now, every experiment shows you a list of the models that it came up with. You can use the experiment view to select the best model, and this will open up the model-specific page that we talked about earlier. Now, ML Studio makes deploying a model super easy. Once you have a model that you like, you can simply select the Deploy button at the top of the screen. And when you click Deploy, it will pop up a dialog that requires you to populate some information about the deployment you want to make. Now, this includes simple things like name and description, but it also asks you to select which compute you want to associate the deployment to. Now, what that means is that when people access your model, the model will be run against that compute that you've selected. So you may choose to use a different compute for your deployment than you did for the experiment. Then, once the model is deployed, a message will be shown telling you so. And that's it. It's that simple. Create an ML workspace, launch the studio, run an automated ML instance, associate it to a dataset, associate to some compute, run a classification experiment, look at the models, deploy the best one, and you're done. And when you're done using the ML Studio, you'll want to clean up the resources that you're using in Azure so that you don't get charged for the systems that you're simply not using anymore. Now, there are two simple ways that you can do that. The first way is that you can delete the Azure ML Workspace resources that you created along the way. That means going through the ML Studio and deleting endpoints, compute instances and clusters, models, datasets, or really just anything that you don't want to use anymore. You can even delete the entire ML workspace if you want. The other way you can do this is to delete the entire resource group that the ML workspace belongs to. This is my preferred way. If you created your ML resources in a single resource group and then made sure that that's the only set of resources that you put in there, deleting the resource group is the quickest and simplest way to purge the system of your entire ML test in one fell swoop. In this demo, we're going to create a classification model, execute an experiment, and then run through and identify the results of the experiment. We'll do that by using the automated ML feature of Azure ML Studio. We'll know we're done when we can explore a completed experiment and view the best model. First, let's navigate to our ML Studio instance in our browser. Okay, so what we want to do here is we want to create a classification model that's capable of classifying a dataset of patients as being diabetic or not diabetic. We can do that manually by creating a pipeline via the designer, but let's make our lives a lot easier and get Azure to do it for us. To do that, we need to use the automated ML feature of ML Studio. So let's go ahead and click on the automated ML option in the left-hand menu. Now this screen shows us all of the automated ML runs that we've created so far. We can edit existing runs, or we can create new ones. In our case, we want to create a new run, so let's go ahead and click on the New Automated ML Run button at the top of the screen. Now we've been pushed into the Create a New Automated ML Run wizard. The first step in that process is that it's asking us for a dataset to use. Now, if you already have a dataset, you can select one. But if you don't have a dataset, you can create one on the fly. So let's go ahead and create one on the fly. We'll actually use a sample dataset from Microsoft to do this. So let's go ahead and click on the Create Dataset button at the top and choose From Web Files option. Now we've been pushed into another wizard. This wizard is asking us for information about the dataset that we want to create. In the web URL field, I'm going to provide the URL for the Microsoft Diabetes sample dataset. The URL is https://aka.ms/diabetes-data. For a name, I'm just going to call this SB Test DSET class demo. Good. Now we'll click Next. Alright, now in the Settings and Preview Wizard step, we can see that the dataset has been loaded because it's showing us information at the bottom of the screen. Most of the defaults on this step are fine, except that we want to change the column headers field to use headers from the first file, so let's do that. And then we can click on Next. And then we can leave all the defaults and just click through to the end of the wizard. And now we find ourselves back in the automated ML wizard. And now we can select the radio button for our new dataset and click the next button at the bottom of the screen. The next step in the wizard is asking us to choose an existing experiment or to create a new one. Well, this is a totally new run, so it makes sense to create a new experiment. So let's select the Create New option. Good. Now we can give our experiment a name. I'm going to call mine SB Test Experiment Class Demo. And now the step is asking us to choose a target column. In our case, we want to predict whether a patient is diabetic or not, so we're going to select the diabetic column from the list. And now the last step in the process is to select a compute cluster. Now you can choose to select an existing one, or you can create a new one on the fly. In the interest of time, I'm going to select a cluster I already have. Good, and now we can click Next. Now what we're trying to do here is predict whether a patient is diabetic or not. That sort of prediction is a classification prediction. The patient is either classified as diabetic or not diabetic. So we want to use the classification task type. But we also want to configure a couple of things. So let's click on the View Additional Configuration Settings link at the bottom of the list of task types. Now in the configuration panel on the right, we'll set the primary metric field to AUC weighted. And we'll set the training job time field in the exit criterion to 0.25 hours, which means 15 minutes. And then we'll set the validation to k-fold cross-validation and the number of validations to 2. And finally, we'll set the concurrencies to 5. And then we can click Save. Now let's click on the View Featurization Settings link. And we'll make sure the Enable Featurization field is enabled, and then we'll click Save at the bottom. Now I'll click Finish. As you can see, this kicks off the run. Now at the very top of the screen is a label that indicates whether the experiment is running. This will actually take quite some time. In fact, it may even take up to that 15 minutes that we configured. So I'm going to cut the video here and I'll come back when it's done. Good. Now we can see that the run is completed. In fact, on this screen we can see a bunch of information about the run. But the most important part is the Best Model Summary box in the top right-hand corner. In this box, we can see information about the best model that was run, which was called the Light GBM model. If we click on the algorithm name, we can see more information, so let's do that. Now this screen tells us that the best model was found in Run 5, and you can tell that from the title of the screen. You can also see a bunch of information about the run by clicking through all the various tabs. Then, if you like the model, you can even deploy it using the Deploy button at the top of the screen. But what we're most interested in is the details of what the model found. So let's start by clicking on the Metrics tab. Now in this tab, you can see several bits of information about the model run that can tell you how close it was to predicting the various actuals that were in the original dataset. Probably the most interesting thing is the confusion matrix. So I've turned that on by clicking on the checkbox. Now let's scroll down to the chart. Now if we look at the confusion matrix chart, we can see how well the model did at its predictions. And what we want is for the top left corner and the bottom right corners to be where the bulk of the predictions land. And that's exactly what we see. So looking at this, we could say that our model is actually quite good at predicting whether a patient is diabetic or not. And that's a simple classification model. In this demo, we're going to create a regression model, execute an experiment, and then run through and identify the results of the experiment. We'll do that by using the automated ML feature of Azure ML Studio. We'll know we're done when we can explore a completed experiment and view the best model. So first, let's navigate to our ML Studio instance in our browser. Okay, so what we want to do here is create a regression model that's capable of figuring out how many bike rentals we can expect given certain conditions, like the day of the week, weather, and so on. We can do that manually by creating a pipeline via the designer, but let's make our lives a lot easier and get Azure to do it for us. To do that, we need to use the Automated ML feature of ML Studio. So let's go ahead and click on the Automated ML option in the left-hand menu. This screen shows us all of the automated ML runs that we've created so far. We can edit existing runs, or we can create new ones. In our case, we want to create a new run, so let's go ahead and click on the New Automated ML Run button at the top of the screen. Now we've been pushed into the Create a New Automated ML Run wizard. The first step in the process is that it's asking us for a dataset to use. Now, if you already have a dataset, you can select one, but if you don't have a dataset, you can create one on the fly. So let's go ahead and create one on the fly. We'll actually use a sample dataset from Microsoft to do this, so let's go ahead and click on the Create Dataset button at the top and then choose From Web Files. Now we've been pushed into another wizard. This wizard is asking us for information about the dataset we want to create. In the web URL field, I'm going to provide the URL for the Microsoft Bike Rentals sample dataset. This URL is https://aka.ms/bike-rentals. For a name, I'm just going to call this SB Test Dset Regress Demo. And now we can click on Next. Good. Now in the Settings and Preview Wizard step, we can see that the dataset has been loaded because it's showing us information at the bottom of the screen. Most of the defaults on this step are fine, except that we want to change the column headers field to use headers from the first file. So let's do that. Good, and then we can click Next. And then we can leave all the defaults and just click through to the end of the wizard. And now we find ourselves back in the Automated ML wizard. So let's select the radio button for our new dataset and click the Next button at the bottom of the screen. The next step in the wizard is asking us to choose an existing experiment or to create a new one. Well, this is a totally new run, so it makes sense to create a totally new experiment. So let's select the Create New option. Good. Now we can give our experiment a name. I'm going to call mine SB Test Experiment Regress Demo 2. And now the step is asking us to choose a target column. In our case, we want to predict the number of bike rentals that we can get given certain conditions. So we're going to select the Rentals column from the list. And now the last step in the process is to select a compute cluster. Now you can choose to use an existing one, or you can create a new one on the fly. In the interest of time, I'm going to select a cluster that I already have. Good. Now we can click Next. Now what we're trying to do here is to predict how many bike rentals we can expect under certain conditions. That sort of prediction is a regression prediction because it's a numeric output that helps us understand how much or how many. So we want to use the regression task type, so let's click on that. Of course, we're also going to need to configure a couple things, so let's click on the View Additional Configuration Settings link at the bottom of the list of task types. Now in the configuration panel on the right, we'll set the primary metric field to normalized root mean squared error. Then, to make the experiment run a little faster, we'll block all the algorithms except random forest and light GBM. And then we'll set the training job time field in the exit criterion to 0.25, meaning 15 minutes, and the metric score threshold to 0.08. And then we can click Save. Now let's click on the View Featurization Settings link. And we'll make sure the Enable Featurization field is enabled, and then click Save at the bottom. And now I'll click Finish. Now, as you can see, this kicks off the run. At the very top of the screen is a label that indicates whether the experiment is running. This will actually take quite a bit of time, so in fact it may even take up to that 15 minutes that we configured. So I'm going to cut the video here and we'll come back when it's done. Good. Now we can see that the run is completed. On this screen we can see a bunch of information about the run, but the most important part is the best model summary box. In this box we can see information about the best model that was run. And if we click on the algorithm name, we can see more information. So let's do that. This screen tells us that the best model was found in run 5. You can tell that from the title of the screen. You can also see a bunch of information about the run by clicking through all the various tabs. Then if you like the model, you can even deploy it using the deploy button right at the top of the screen. But what we're most interested in is the details of what the model run found. Let's start by clicking on the Metrics tab. Now in this tab, you'll see several bits of information about the model run that can tell you how close it was to predicting the various actuals that were in the original dataset. You can click on things like the predicted versus true chart or the residuals chart, and see additional information that can be very useful to deciding if your model is any good. Of course, you can also click on the explanation tabs at the top of the screen. And then click on the Aggregate Feature Importance tab. And when we do that, we can actually start to see information about which fields had the greatest impact on bike rentals. In this case, it was the working day and temperature. So from that, we can determine that if the weather is good, or on a working day, we'll likely get more bike rentals. And that's a simple regression model. So in this course, we've worked with the Azure ML Studio and learned about the features of some of the Azure ML services. We did this by exploring Azure Machine Learning Services, features of the Azure Machine Learning Studio, computer and custom vision services and their uses, Azure Face Service and Form Recognizer services and capabilities, Azure ML workloads and compute resources, creating and managing datasets and pipelines, model training algorithms and running an experiment, and classification and regression model metrics. In our next course, we'll move on to work with the Azure ML Studio and learn about the features of some of the Azure ML services.